GameSide.com. GameSide.com.
Hello and welcome to Binary Trees on Disk. We're going to create a database to track online game user accounts. You need sorted access to your online game user accounts. A hash table is not sorted. It does not work if you need sorted access. Binary trees are slightly slower than a hash table, but do provide sorted access. What we need to do is map a binary tree to a disk drive. We're going to have to write records to a sector on the hard drive and read records back from the hard drive. We're going to map this binary tree to disk sectors on the hard drive. To map a binary tree to a hard disk drive, think about this. A disk drive is an array. Disk drives are block addressable. We must read or write a sector at a time. And a sector is an array of bytes. A 512 byte sector can be divided into 4 records of 128 bytes each. A disk sector is an array of bytes. At byte offset 0, you can store 128 bytes, 0 through 127. At byte offset 128, you can store another 128 bytes between 128 and 255. At 256, another record of 128 bytes, bytes 256 to 383. And at byte offset 384, there's another 128 byte record. Map one of these 4 records to a sector on the disk drive. Records 0 through 3 can go in sector 0. Records 4 through 7 can go into sector 1. Records 8 through 12 can go into sector 2. Records 12 through 15 can go into sector 3. All the way down to sector N, where you can have records N times 4 and 3 more records. A hard disk or file is then an array of sectors. They're even numbered: sector 0, sector 1, sector 2, all the way to sector N. A disk drive is an array, and you can map a binary tree to that array. We know from the hash table bucket approach, a disk sector can be divided into multiple records. For binary trees, treat each of these records like an array slot. With 4 records each, sector 0 contains records 0 through 3. Sector 1 contains records 4 through 7, and so on. The math is actually simple. Record 9 is in sector 2. 9 divided by 4 equals 2. Record 15 is in sector 3. 15 divided by 4 is 3. Record 100 is in sector 25. 100 divided by 4 is 25. We learned in the lesson on binary trees how to map a binary tree to an array. All we have to do is calculate the sector number when we want to read a record from the binary tree array. If you want to go to slot 15 of the binary tree, you've got to read sector 3. That's all there is to it. A simple little math will tell you which disk sector to retrieve a binary tree record from. RAM memory arrays are easy. To access slot 14 of a RAM memory array, you just go to Data, Subscript 14, and assign it 42. Disk arrays need a little integer arithmetic. Think of the disk drive as a virtual array. Whatever was in slot 14 of the RAM memory, you can calculate which disk sector slot 14 of the RAM memory should be in. Think of slot 14 this way. You've got to read sector 3. 14 divided by 4 says record 14 of our RAM memory array. It's got to be on disk sector 3. You can even use some modulus arithmetic. 14 modulus 4 equals 2. That means this record should be at offset 2 in the sector. 2 times our 128 byte record says at byte offset 256 is where 42 should go. So let's insert 42 at byte offset 256 in sector 3 and then write sector 3 back to the disk. Do you see how I did that? Slot 14 of the array, where we're mapping our binary tree, calculated out to sector 3 on the disk drive. Within sector 3, it calculated it out as virtual record 2. So we went to that byte offset and stored our data in that byte offset. And then we wrote the sector back out. We just updated record 14, virtual record 14, in our binary tree. The use of the modulus operator to calculate. Where is the record/array slot 100? Well, 100 divided by 4 equals 25. Record 100 has to be in sector 25. Within sector 25, where is that record? 25 modulus 4 equals 0. 0 times our 128 byte record says at offset 0 is where we should find record 100. So 100 is in sector 25 at byte offset 0. You see what we're doing? You almost need to think of it as a virtual array. Think of the disk file as a virtual array. Mapping a binary tree to an array says, I want to store something in record 100 of the binary tree. If it was RAM, you just go to slot 100. If it's disk, you've got to calculate where record 100 would go, sector 25, and then within that sector, what offset would the record go? And that was byte offset 0. Takes a little bit more math, but you can map a binary tree to a disk drive just like you can store a binary tree in RAM memory. I used hard-coded values like sector size 512, record size 128, and 4 records per sector. Using variables is much better than using hard-coded values. At some point, you want to set up a int sector size to tell you how many bytes are in each sector. Let's say 2048. You want to set up an int record size to tell you how big each record is. You want to set up an int number of records to tell you how many records you're storing per sector. Note, diagram was not updated for 8 records per sector. This diagram is the old diagram. But once you have these constants set up, and that's the way to code this, you can use the modulus operator to do your calculations. If you want to find record or array slot 100, it's in 100 divided by number of records, and says if there's 8 records per, then it's going to be in sector 12. And when you want to find the offset within that sector, you do 100 modulus the number of records, and it says it's going to be in record offset 4. Using the math based on these variables, I could say that 100 is going to be in sector 12 at byte offset 1024. Remember, each record is 256 bytes in this scenario, so that's byte offset 1024 is where you want to store record 100. It's simple math, people. All you got to do is calculate based on the sector size, the record size, and the number of records where something is going to be stored on the hard drive. In RAM memory, a binary tree can be mapped to a simple one-dimensional array. Recall the formulas. If the root starts at index 0, the left child will be at 2 times index plus 1. The right child will be at 2 times index plus 2. And the parent will be at parentheses index minus 1 end of parentheses divided by 2. In disk memory, map/calculate exactly the same way, then calculate the sector. The right child of 70, here's 70 at record 2 of our array. The right child of 70 is at 2 times slot 2 plus 2, or index 6. The right child of 70 should be at index 6. And there you see, the right child of 70, 80, is at index 6. But you got to add a little math for a disk drive. 6 divided by 4 equals 1. That means record 6 has to be in sector 1. 6 modulus 4 equals 2. That means in sector 1, it's 2 records down. 0, 1, 2. 2 records down in sector 1 is our virtual slot 6. 80 is in sector 1 at record offset 2 within that sector. 70 is at index 2 of the 1D array. Where would 70 be located on the disk drive? 2 divided by 4 says 70 should be in sector 0, and 70 is in sector 0. 2 modulus 4 equals 2, so 70 is 2 records down from the top of the sector. Record offset 2 within this sector 0. Look at 80. 80 is at index 6 of the 1D array. 80 would map to slot 6 of the 1D array. Well, 6 divided by 4 equals 1. So 80 should be in sector 1. 6 modulus 4 equals 2. So there's 80 in sector 1 at record offset 2. Each sector has a record 0, a record 1, and a record 2, and there's 80 in record 2. Just takes a little bit of math to map a 1D array to a hard drive and sector numbers. To map a binary tree to disk using the 1D formulas, let's do a find on record 40. Well, how do you locate something in a binary tree? You start at the root and you search down the tree until you find what you're looking for. If we're going to do a find on 40, let's start at the root. The root will be at index 0. 0 divided by 4 is 0. 0 modulus 4 equals 0. We're going to read sector 0 and look at record offset 0. Here we are. Sector 0, record 0, there is the root of our binary tree, the 50. 40 is less than 50. 40, what we're looking for, is less than 50. So we need to go left. The left child of the root is at 2 times 0 plus 1. The root is at index 0. 2 times 0 plus 1 says we need to go to index 1 to find the left child. 1 divided by 4 says the left child will be in sector 0. 1 modulus 4 says the left child will be at record offset 1. So we go to sector 0, record offset 1, and we look at that value. Sector 0, record offset 1 is the 25. The left child of 50 is in record offset 1 of this sector. The 25 means we do a 40 less than 25. That is a false statement. When what we're looking for, 40, is less than the node we're looking at, 25, we go right. Going right in a 1D mapping of a binary tree says 2 times 1 plus 2. That is index 4. The right child of 25 is at index 4. 4 divided by 1 says we should find the right child in sector 1. 4 modulus 4 is 0. So in sector 1, record offset 0, we will find the right child of 25. We read sector 1 into RAM memory. We look at record offset 0, and we find our 40. After reading sector 1 and looking at record 0, 40 matches a 40, we're done with our search. Big O. Big O notation for a binary tree says we should be able to find a record in order log n times. This means finds will have to read at most log base 2 of n disk sectors. A 10 level tree means we're going to have to read 10 minus 1 or 9 sector reads. Why the minus 1? Because sector 0 has 2 levels in it. Normally you'd have to do 10 sector reads to read 10 levels of the tree. But all of the first 2 levels of the tree, 50, 25, and 70, are located in sector 0. So we get to go through 2 levels of the tree for sector 0. Then as we work our way down the tree, we'll have to read basically 1 disk sector per level of the tree. 10 level tree, 9 sector reads. This example assumes 4 records per sector. That is, of course, entirely dependent on sector and record size. Do not hard code. Use variables. Be sure to allocate enough dissectors for the maximum number of levels. If you want 10 levels to your tree, you need 2 to the 10th or 1024 records. If you need 1024 records, 1024 divided by 4 equals 256 sectors required. Recall that 1D binary trees only work well with balanced binary trees. Might not be a good idea for disk-based binary trees. The 2D trees may be better for disk-based binary trees. Let's look at mapping a binary tree to a 2D array or a table, and then mapping that table to a hard disk drive. Recall, in RAM memory, a binary tree can be mapped to a 2D array, aka a table. If you put the root in row 0, the left column is the row of the left child. The right column is the row of the right child. The left child of 50 is row 3 of the table. The right child of 50 is row 6 of the table. And there at row 6, you see the right child of 50, 70, is in row 6 of the table. You set up a column for the left and right childs, and these numbers represent the row of the table. The -1 means it doesn't have a left and right child. You can see 15 as a left and right of -1. 15 at this point doesn't have a left or right child. In disk memory, a row is a record. Put as many records as will fit per sector. In the example above, let's say 5 100-byte records, or rows, will fit into one 512-byte sector. We'll go ahead and leave the 12 bytes unused in each sector. We're going to map 5 records or rows from this table per sector. And you can see I put 5 records in sector 0 and 5 records in sector 1. With 5 records or rows per sector, you can calculate each sector. Row divided by 5 will calculate the sector number. To calculate the row offset, row modulus 5. Where is the right child of 50? The right child of 50 says it's in row 6. Do a 6 divided by 5 and say I need to read sector 1. I'll do a 6 modulus 5 and say record 1, sector 1 is where I should find the right child of 50. And if you follow that down to row 6, sector 1, record offset 1 is where the right child of 50 is located. 70 is the right child of 50. Once again, the mapping to RAM is the same. You've got to do these 2 extra calculations. Map a binary tree to disk using the 2D array left and right columns. Let's find 40 in our 2D table that is mapped to the hard drive. Well, if we put the root at row 0, that means we have to read sector 0 and look at row offset 0. So we'll start our search for 40 at the root. That's where we always start our search, at the root of the binary tree. So I'll read in sector 0, and at byte offset 0, I will see that 53 and a 6. 40, of course, is less than 50. That is a true statement. We need to go left on the tree. The left child of 50 says I should go to row 3 of the table. 3 divided by 5 says that should be located in sector 0. 3 modulus 5 says it should be at record offset 3. So what we need to do is look at sector 0, row offset 3. The left child of 50 is in sector 0, row offset 3, and there we find our 25. I don't even have to read a new sector in. It's in the same sector, so that saves me a sector read. At row 3, 40 less than 25 is a false statement, so we need to go right. We need to go to the right child of 25. The right child of 25 is row 5. The right child of 25, the values greater than 25, are at row 5. Well, how do we get to row 5 of our 2D table? We do a little math. 5 divided by 5 equals 1. That means the right child is in sector 1. 5 modulus 5 is a 0. So we're going to read sector 1, and at row offset 0 of that sector, we are going to look for our data. So there's sector 1 right there. There's row offset 0. It contains a 40. In sector 1, row 0, 40, what we're looking for, matches 40. What's in that row? We are done with our search. Big O, order of log n, means find will have to read at most 10 sectors for a 10-level tree. Sometimes it's less than 10. Let's say we were doing a search for 15. A search for 15 would actually go even faster. We would start here at 50. 15 is less than 50, so we'd go to row 3. Row 3 is sector 0. It's already in RAM memory, so we'd go to row 3. Look at the 25. 15 is less than 25. So that says go to row 1. Row 1, the left child of 25, is in the same sector. Go to there and we'd find our 15. It turned out all 3 records we needed to look at were in sector 0. So after reading only one disk sector, we were able to find 15 in the tree. It's a simple mapping. We map a binary tree to a 2D table. We then map the 2D table to a hard disk drive and sector numbers. When we have the row of our binary tree, we then calculate the sector number and the record offset within that sector to search the binary tree. This example was done assuming 5 records or rows per sector. That, of course, is entirely dependent on sector and record size. Do not hard code. Use variables. Allocating space is much easier for a 2D binary tree on disk than a 1D binary tree on disk. Use the maximum number of items or rows in the tree and divide it by the rows per sector. That equals the needed sectors. If you know you're going to store 1,000 items in the tree, you need 1,000 rows. All things considered, using a 2D array or table to store a binary tree to disk is a better solution over a 1D. If you're going to store a binary tree as a 1D, it's got to be balanced or disk space is not used efficiently. I'd much rather map a 2D array or table to hard disk drive than a 1D array. There is a big issue when an unbalanced binary tree is stored on disks. Searches can take vastly different number of disk sector reads. A search down one side of the tree that has 10 levels reads 10 disk sectors. A search down the other side of the tree with 3 levels reads 3 disk sectors. Balanced tree structures are studied in future lessons. But for now, let's live with this problem and understand the problem. Unbalanced binary trees on one side could take far more disk sector reads than a search on the other side of the tree. A 2D array table does handle an unbalanced binary tree better than a 1D array, but that's for the amount of disk storage needed. A 2D binary tree mapped to disk uses much less memory when it's unbalanced than a 1D array, but it doesn't solve the problem of unbalanced trees. It can still take far more number of disk reads when the tree is unbalanced. A database at its core is a data structure stored on a disk drive. For the fastest access, store the data in a hash table using the bucket approach. For sorted access, a tree structure is required, and you're going to have to map that tree to a disk drive. While technically this is not a database course, we are studying the foundations of databases. Sorted structure stored on a disk is what the core of a database is. While we're learning how to store binary trees on disk, we're learning databases from the bottom up. Let's look at the layered approach when it comes to storing binary trees on disk. Remember, we're trying to create a database to track online game users, and we need to store those uses in a sorted order. The trick to storing a binary tree on disk is converting to and from a 2D array in RAM memory to an array of bytes for disk memory, mapping multiple rows from the 2D array to a disk sector on the drive. This is a diagram of RAM memory of the 2D array. In RAM, data is stored in records as strings, doubles, and ints. This is a 2D array containing integers. It could also contain strings and doubles and other data types. On disk, we need to be stored in sectors as an array of bytes. A disk is an array of bytes. So in sector 0, I'm going to map 5 records to sector 0 as an array of bytes. In sector 1, I'm going to map up to 5 records per that sector in an array of bytes. We have to convert for how we store data in RAM to how we store data on the disk. Let's look at a RAMtrie record first. One record in RAM memory is a row of the table. One row equals one player count. Now there could be more fields in this record. All fields are converted to and from 100-byte arrays. We can store up to 1,000 nodes, so we'd need 200 disk sectors. 1,000 divided by 5 is 200. 200 disk sectors will allow us to map 1,000 rows of this table. Now this example we're going to look at does contain some hard-coded values. As I keep saying, it's better to use constants. Let's say we had a sector size of 512, a record size of 100, and a sector size of 5 records per sector. Let's use this idea of constants when we are mapping our tree record to a disk sector. In RAM, a table is stored in one block. One binary 2D tree equals 1,000 player records. On disk, we must split 5 rows into 512 byte blocks and store it in 200 sectors. Every system is different. Be sure to be flexible on sector record size. That's why we want to use constants. So if we need to change it for a different disk drive, it's easy to change. The direct approach to mapping a 2D array to a disk drive is to write 2 functions. We're going to write one function to convert 5 tree records to an array of bytes. So a function to go from 5 tree records in RAM memory all the way to an array of bytes. Then we'd need another function to convert an array of bytes to 5 tree records. So we'd go from an array of bytes on the hard disk drive to 5 tree records in RAM memory. These would need to be large, complex functions. We're making a big jump from a record in RAM memory to a row of bytes in disk memory. The layered approach says put a layer between RAM and disk. Convert the 5 tree record objects to and from 5 simple string objects. Convert the 5 string objects to and from a 512 byte array. This is the extra layer. I'm going to convert from a RAM-based record to a simple string. Then from a simple string, I'm going to convert to an array of bytes. I'm going to convert from an array of bytes to a simple string, then from a simple string to a record in RAM. See how we insert a layer between the complex 5 tree records in RAM memory and a simple byte array on disk? The 5 string objects are an intermediate step. Not only does this break a larger problem into smaller pieces, it helps simplify storing other data structures to disk. Reuse hash table functions that convert to or from strings. We already wrote this code. If you recall from the bucket approach of hash tables, we wrote code to convert from strings to arrays of bytes and from arrays of bytes to strings. These would be the same functions we used in hash tables. The only new thing we have to do is convert from a row in RAM memory to a string, and from a string to a row in RAM memory. This is code reuse, and it makes implementing data structures to disk drives easier. That extra layer isn't more work, it actually means other data structures will be easier to write to disk memory. Now, how would you do this? The simplest approach would be to take our tree record, which must have a key and a left and right child offset in the table, and maybe some more data. We need to map this to a string. Fixed length fields would be the easiest way to do it. We'd copy/convert the key to characters 0 through 9 in our string. And we'd copy or convert the left field to characters 10 through 19. The key went to here, the left field went to there. You'd copy and convert the right field to characters 20 through 29. Boom. And if you had more data stored in the record, which you likely would have, you would copy and convert those fields to characters 30 through 99 in the string. We'll space fill any unused characters in a field or at the end of the string. So a function tree record to string and a function string to tree record are not hard. We'll use the built-in functions to convert to or from strings. We'll just say, hey, let's take that field and you get these characters in the string. We'll take that field and you get these characters to the string. Most of this work is just converting from one format to another format. We're going to take integer fields and convert them to string characters. Fixed length fields are one way to convert data in RAM to bytes stored on disk. There are many different approaches. Be flexible. Strings as a middle layer is not a requirement, but they are easier to use and system independent. The functions string to byte array and byte array to string are trivial. A string is essentially an array of characters, and converting between a character and a byte is as easy as it gets. Use the same functions created for hash buckets, and you've solved half the problem already. To recap the layered approach, 4 functions are needed. We need to convert a RAM record to a string. Take a RAM record, a record is a row of the 2D table, and convert it to an array of characters. Easy enough. We then need to convert the string to an array of bytes. Converting a character and a string to a byte is super simple. Then going back the other way, we need to convert from an array of bytes to a string. Again, very easy, and we already did it for hash tables. Then we have to take a string and convert it to a RAM record, a row of the 2D table. This layered approach lets us reuse software from hash tables. All we have to do is write the new functions and reuse the functions we already wrote for hash tables. None of this is set in stone. The extra layer of strings, the fixed length fields, converting numeric fields to characters, the layered approach is just one way to split a larger problem into smaller problems. There are many other solutions to this problem. But overall, what I'd like you to think about is breaking larger problems into smaller pieces. Going directly from a row of the 2D binary tree straight to an array of bytes is a bigger problem. Split that bigger problem into 2 smaller pieces. From record to string, string to byte. From byte to string, string to record.
GameSci.com.